Hi, my name is Yujin Huang, and welcome to our skills video. We are MuddSub, Harvey Mudd College's RoboSub team, and we'll be presenting our current hydrophone design under the sensor optimization category. Our presenters for this video are in the left section, namely, I will be going over the subsystem overview and electronic design of the hydrophone board. Jordan will be covering the current algorithms that we are using to locate the robot's position. Alex will be discussing the Teensy firmware, and Francine and James will be focusing on our planned testing for our current hydrophone design. On the right are team members who are heavily involved in the design and implementation of the hydrophone board. Seth Isaacson and Caleb Norfleet mainly designed the hydrophone PCB and Teensy firmware, and Daniel Yang has implemented the first iteration of the signal classification algorithm. The main goal for hydrophones is to locate the pinger and use this information to estimate the relative position of the robot. For context within the competition, the pingers in the pool send out pulses of sound between 25 to 40 kHz. And, if implemented and denoised correctly, the hydrophones can help derive the position of the robot with respect to the pinger source. The overall design is seen in the block diagram above. The system design comes with two main components, the analog and the software design, which will be detailed further in later sections. Specifically, our current design uses 4 hydrophones, and then the analog signal goes through a charge mode amplifier and a multiple feedback bandpass filter in order to eliminate noise that is outside of the pinger's range. Then the signal gets passed through an ADC, and Teensy 4.1 firmware is written. Then the signal passes through a digitally isolated USB port, which connects to our main current computer, the Jetson AGX Xavier. These digital signals are then passed through our implementation of the S-Spirit algorithm, which is used to find the direction of arrival and eliminate noise and the signal subspaces. With these pieces of information, we can extract the robot's position in relation to the pingers. Now let us transition into talking about our competition strategy. We sample analog data from our 4 Teledyne resin TC4013 hydrophones. Then the signal will pass through an analog front end and an ADC. The digital data is then sampled on a Teensy 4.1 microcontroller. We use a Teensy as our choice of microcontroller for this board for its easy-to-use interface and robust connectivity. Our hydrophone PCB is highly sensitive to noise, and to prevent potential ground interference and noise from our signals, a USB digital isolator is used before going into the Jetson. The analog signal goes through a 2-stage front end, including a charge amplifier and a multiple feedback bandpass design. We implemented a charge amplifier as our first stage in order to produce an output voltage that is proportional to the charge generated by our hydrophones. Charge amplifiers are useful to amplify signals with piezoelectric transducers, such as hydrophones, as charge amplifiers minimize the effects of interconnect capacitance. Additionally, for our second stage, we decided to use a multiple feedback bandpass filter for 25 to 40 kHz instead of other common architectures like Sallen-Key, due to its ability to achieve a high quality factor and high noise gain. Since the ADC expects a differential input, the second stage additionally converts the single-ended signal to a differential one. In addition to the analog filtering, some other important features in our hydrophone board include choosing an ADC, specifically the ADAR7251, that has 2 programmable gain stages to allow us to adjust the amplification depending on the distance from the pinger. We also included a sub-circuit for a battery voltage monitor by using a voltage divider and a simple buffer with an RC anti-aliasing filter. And lastly, the 4 channels are sampled synchronously.
The hydrophone's algorithm we will be using is called S-Spirit, which stands for Estimation of Signal Parameters via Rotational Invariance Techniques. The reason we settled on S-Spirit is because it is able to provide the most accurate direction of arrival in noisy environments. It is important to have a robust algorithm that can filter out noise, as the motors that a robot uses produce frequencies that are within the same range of frequencies that the pingers are at. This means that a simple bandpass filter will not remove all undesired noises from the signal. Note that we additionally assume the signal we receive takes the shortest path from the pinger to the hydrophone, which would require us to accurately find the beginning of the signal. So we isolate the direct path to the hydrophones by thresholding in the time and frequency domain. Because the pinger signals will echo off the sides of the pool, the algorithm will wait to hear a moment of silence before reacting to pings. After it gets its initial reading, it will ignore all other signals as they will be presumed to be echoes until 2 seconds later when the pinger chirps again and another pinger reading can be made. The raw digital signals from the hydrophones is put into a matrix with the data points from the signals in each column and a row for each of the hydrophones. A covariance matrix is created from the original to compare the values of the signals in each position. Then we use eigenvalue decomposition to separate the signal subspace from the noise subspace. The eigenvectors that correspond to the highest eigenvalues span the signal space. Finally, maximum likelihood estimation is used in order to estimate the DOA, direction of arrival, of the pinger signal.
The Hydrophones firmware has two primary functions. The first is configuring the settings on the ADC, such as the sampling rate, onboard amplification, and the output format. The second is the sampling of the digitized data. At initiation, the settings of the ADC are configured using SPI, then the chip is pulled to ensure that there aren't any errors. When sampling, the 4 channels of the 16-bit data is received as 8 bytes of parallel data. This is then sampled at a constant frequency and rearranged into 4 16-bit samples. Due to the high-speed rate of sampling of 2.4 MHz, the GPIO register is sampled all at once, and the samples are reconstructed later.
Now let's talk about development and testing of the hydrophone board.
So far, we have produced a physical PCB and soldered all of the components onto it. Going forward, we plan on further developing the electronic component of our hydrophone system. We would like to formalize the board, ensuring that all of the components have proper specs for our purposes, and that the individual subcircuits work as intended. We also plan on implementing additional remote reset capabilities to allow for better troubleshooting both in and out of the pool. We also have plans for testing the electronic component of our hydrophone system. We will conduct our testing by connecting these test points to an oscilloscope and tracking the outputs we receive from the analog portion of our circuit. We will provide signals to the hydrophones in various ways. We will first check the outputs we receive when no signal is provided to the hydrophones. We will also hit the hydrophones on solid objects to produce a signal and physically hold it against signal sources like pingers. At this point, we have developed firmware that runs on our Teensy for transmitting data from the hydrophones to our Jetson computer. We also plan on testing this firmware. We will first test the board without the hydrophones plugged in to verify that our firmware is able to send data to the rest of the robot. We will then test the system with the hydrophones plugged into the board. We will follow a similar procedure to testing the electronic components, giving the hydrophones signals ranging from no input to hitting them against solid objects to holding them against signal sources and verifying that the outputs from the sensors are reasonable.
Beyond electrical and firmware testing, we also plan to thoroughly test our signal classification algorithm. This algorithm is still in early development, so we haven't fully planned out our testing of it. We're planning to implement the SBRT algorithm, as we talked about earlier in this presentation. We have a summer research team working on this project now, so the development is in process. As for how we're going to test, we plan to use both simulated and real hydrophone data. At this point in our development, we have created a signal generation tool for producing simulated hydrophones data. Using a set of given parameters, it creates signal data, then adds random reflections, and finally adds a random noise matrix to produce simulated hydrophones data. Our simulated data will consist of multiple sine waves, an offset in the amplitude, and Gaussian noise. We also plan to use real hydrophone data from other teams as well as data we collect ourselves to test our algorithm. Eventually, we will test SBRT against other algorithms to ensure that it is the best choice for our use. Some other algorithms that we might try to implement for comparison are music and FFT.
Thank you for listening. This Hydrophones project has been a great opportunity to learn more about different subjects, from signal processing, learning how to write robust firmware for the Teensy, and PCB and general electronics design. We hope that you enjoyed this presentation. Thanks for listening.